Hello everyone, today we'll discuss common source amplifier with the load as a current source. Okay, in previous lecture we have seen that a common source amplifier with a resistive load, and in that configuration we got AV equal to minus GM RD. Okay, so to increase AV, how can we increase AV? By increasing the GM, one option this, and second is by increasing the RD. Now first, if I am increasing GM, how can we increase GM? By increasing the current ID. Okay, by increasing the ID current. If I am increasing current ID, then power will increase, the power dissipation will increase, which is a problem. Second, by increasing W by L. Okay, by increasing W by L. If I am increasing W by L, then GM will increase, but capacitance will increase, and bandwidth will reduce. But what we want constant bandwidth. So this is a problem. And the second case, we can increase AV by increasing the RD. Okay, so if I am increasing RD, what will happen? V0 will reduce. Okay, V0 will reduce, and because of which the transistor can go in triode region. Okay, so how V0 is reducing? Let's see its configuration. This is RD and V in, and this is V out, VDD. Okay, so apply the KVL on this side. We will got V0 VDD minus ID RD. Okay, RD is increasing, so V0 is reducing. So V0 is reducing, so my VDS reducing. VDS is reducing. Since VDS reducing, transistor can go in triode region. Okay, in triode region it can go. Because it is going in triode region, so the voltage swing limit will reduce. Voltage swing limit will reduce. Okay, so this is the problem while increasing the RD. So we can't increase RD also. So what is the way to increase the gain? Okay, so if I am increasing RD, equal to infinite. Okay, if I am making RD equal to infinite, if I am increasing RD equal to infinite, and the current is flowing constant current, ID equal to constant, so gain will increase. Since RD equal to infinite, how can we got such thing? By using a current source, ideal current source, right? A ideal current source ID I am using. Okay, so this will give infinite resistance and a constant current. Okay, so let's make the full configuration. This is V in, VB and VDD and this. Okay, so when I will make it a small signal analysis I will do, then this will become open circuit. So it will look like this, and I am doing the small signal analysis of only for this, and sorry, this is V in, this is VB, and this is V0. Okay, since you can see there is a no flow of current, so VDS will become equal to 0. So this transistor can go into the okay, see, it's fine for the what time it is getting at the small signal analysis time, it is getting open circuit, so it's fine. Okay, if I am using something in the normal, not in small signal analysis, it is becoming open circuit, so that time it will become what? It will give VDS equal to 0. Okay, VDS will become equal to 0. So our transistor can go in what region? Triode region. So which can be a problem. There will be no amplification because the transistor is in triode region. For amplification we use what region? Saturation region. But in this case, in this current source, in small signal analysis time, we are getting the open circuit, and in normal time we are getting current. So it is good. Okay, right? So let's draw for this small signal model of this circuit. Okay, okay, so this is my plus minus VGS, and there VGS, there it is, V in. Okay, V in is there, and then GM VGS, and source is, okay, ground, and there R naught. We are considering channel length modulation. Case I am taking lambda is not equal to 0, and this is R naught. On this side V naught is present, and see, from V naught to ground, this VDD will become ground in small signal analysis time, so it will become open circuit. So it is open circuit. Okay, so how much gain it will give? It will give VGS equal to V in. Okay, so apply the KCL. The voltage across this R naught is V naught, so applying the KCL on this node, I current is flowing through this, so GM VGS, okay, plus I equal to 0, and GM VGS is V in, I is equal to V naught by R naught equal to 0. Okay, so V naught equal to minus GM V in R naught. So V naught by V in equal to minus GM R naught. So gain AV is equal to minus GM R naught. Okay, so when we are using a current source as a load, we got gain equal to the maximum gain. Maximum gain means internal gain of this transistor. You can see R naught is the internal resistance of this transistor. So this is the gain. So now how can we build a current source? Okay, so to build a current source which can give a constant current, okay, how can we build that? See, in MOSFET characteristics, this is my VDS, its ID, and see, so in this is the saturation region, and this is triode region. Okay, this is triode region. What type of current we want for making a current source which can give a constant current? The constant current we want, right? So there is constant current in what region? Saturation region. So we can build a current source with using a MOSFET, by using a MOSFET in saturation region. Okay, let's make. So for this, making the current source, can we use NMOS for that or PMOS? Let's see. If I am using NMOS, this is my NMOS, VDD, and from this V naught I am taking, I am giving VB in such a way that this transistor is going into saturation region, and V in is there, and this is V bias. Okay, so can we use this NMOS for the making the current source? Let's see. At V naught I will got output like this, right? What we want a current source which can give constant current. Okay, but in this case you can see that VGS is equal to VB minus V naught, and you can see V naught is varying, so VGS will vary VGS is varying, so ID will vary, so I am not getting a constant current. So I can't use a circuit in by using NMOS for the current source. Okay, so what can we do? So let's try PMOS. Okay, we are using PMOS. Now see, VGS. VGS is equal to how much? VB minus VDD. VB is constant, which we are giving. VDD is constant, right? So VGS is constant, so I am getting a constant current ID, right? So I can use PMOS for making the current source, right? Okay. Now, okay, let's calculate the resistance through of this MOSFET. And see, we are taking VB and VBIS in such a way that this transistor M2 and M1 will be in saturation region. VB I am taking in such a way that M2 is in saturation region. VBIS I am taking in such a way that M1 is in saturation region. Okay, let's calculate the resistance of this M2. This is R. Let consider this is R. Okay, so for that, let's make a small signal model for this PMOS M2. Okay, so this is plus minus VGS, and there is a, this will become ground, VG at gate terminal, and the source terminal is at source terminal is VDD, so it will become ground, and at drain terminal is V0. Okay, so this is my drain terminal, and see, source to drain, current is flowing from source to drain. So this is source, so this is my source, and this is drain, and source to drain the current is flowing. So source to drain current is flowing, it is GM VGS, and I am considering the channel length modulation, so R0 2. Okay, the internal resistance. Okay, and this is my V0. So at this terminal we have to apply Vx, and Ix is flowing, and the R out, the R will become equal to Vx by Ix. Okay, see now VGS equal to 0 from this. Okay, VGS equal to 0, so it will become 0. So this is open circuit. It is open circuit, so how my circuit will look? It will look like this. R0 2, and there is a voltage Vx, and a current is flowing Ix. Now apply the KVL. Vx equal to Ix R0 2. So my Vx by Ix equal to R0 2. So R equal to Vx by Ix, so it is equal to R0 2. So this is providing R0 2 resistance, right? Now let's calculate the gain of this circuit. To calculate the gain, let's make a small signal analysis. Let's do small signal analysis of this whole circuit. After doing the small signal analysis, I was getting a resistance of this R0 2. Okay, so now do the small signal analysis for this. It is my Vin, and plus minus VGS, and this is GM VGS. Source is ground. Okay, source is ground, and source is ground. The resistance, we are considering the channel length modulation, so it is my R0 1, and this is V0, right? V0, and see, from V0 to ground, which is VDD, the resistance offered by this M2 is R0 2. So R0 2, R0 2. So this is R0 2. Now okay, so now apply the KVL on this side. So my VGS is equal to V in 1, equation 1. Okay, and now okay, so apply the KCL on this side, on this node. let current flowing through this I1 and current flowing through this I2. Okay, and the voltage across this R02 is V0, and through this R01 is also V0 voltage across this R01. Okay, so now apply the KCL on this node. So it is GM VGS plus I1 plus I2 equal to 0, and so this is my, so it GM VGS is V in calculated, and I1 will V0 by R0 1, and plus it is V0 by R0 2 equal to 0. So V0 into 1 by R0 1 plus 1 by R0 2 equal to minus GM V in. Okay, so V0 by V in equal to minus GM divided by 1 by R0 1 1 by R0 2. Okay, or we can say minus GM R0 1 parallel R0 2. Why it is R0 1 parallel R0 2? We know that 1 by R equal to 1 by R0 1 plus 1 by R0 2. Okay, so R will become equal to 1 by R0 1 plus, sorry, 1 by R0 2. So R0 1 we can say R0 1 R0 2, like this we can say. So that's why we can say it is parallel, right? So in this way we can calculate the gain. So let's, gain AB we calculated is equal to minus GM GM is the gain for this only. Okay, so I am calling it GM1. So AV equal to minus GM1 into R01 parallel R02. This is gain. Now calculate R out resistance. Okay, to calculate R out resistance we have to remove this V in. Okay, and at output side we have to apply Vx. So this is Vx, and current is flowing Ix through it, and this is ground. Okay, so VGS equal to 0. Since VGS equal to 0, what will happen? This will become open circuit. Current will become 0, and it will become open circuit. So now how my circuit will look now? It will look like this: R01, R02, Vx, Ix. Okay, so the voltage across this and this is Vx, right? And now apply the KCL on this node. So let current is flowing through this is I1 and through this is I2. So Ix equal to I1 plus I2. Ix equal to how much? I1 is Vx by R01, and I2 will Vx by R02. So Ix equal to Vx 1 by R01 1 by R02. So Vx by Ix is equal to how much? 1 by R01 R02, or we can say R01 parallel R02. So this is R out. So R out, how much I got? R out equal to R01 parallel R02. Okay, so AV for this circuit is equal to minus GM1 R01 parallel R02, and R out resistance is equal to R01 parallel R02. So this is the answer for common source amplifier with load as a current source, and the current source I am making with the help of the PMOS transistor. Okay, so it's very easy to calculate the gain. See the resistance offered by it R naught. Okay, and we know that the resistance will be coming in parallel of this. Okay, so we know for the common source amplifier with resistive load, AV is equal to what? GM1 R naught parallel RD, right? This is the gain for the resistive load we are taking that time. The gain is this. So in this case, what I am getting in place of RD, I am getting R naught 1. So AV equal to minus GM R naught 1 for this MOSFET and for this R naught 2. So simple it is to calculate. And the resistance for the resistive load, what I was getting that time, that was R out equal to R naught parallel RD, right? In this case, in place of RD, you are getting R naught 2. So simple, R out equal to how much? R naught 1 parallel R naught 2. Simple. So this is all about the common source amplifier with load as a common current source. So thanks a lot for watching the video, and if you have any doubt, you can text me. Thank you.